Hello, my name is Berti and I'm an astroparticle PhD student at SISSA in Trieste. Today I'm going to talk about our work, constraining beyond Lambda-CDM models with 21 cm intensity mapping forecasted observations, combined with the latest CMB data. Let's start with a bit of an introduction. The standard model for cosmology is the Lambda-CDM model, which has proved to be in very good agreement with the majority of cosmological observations. However, theoretical puzzles on the nature of dark energy and dark matter and tensions on parameters constraints from different probes still need to be addressed. For dark energy, in the last decades, a plethora of different models alternative to Lambda-CDM has been proposed and studied. At the state of the art, all the results are broadly compatible with Lambda-CDM, but upcoming observations such as Euclid and SKA are expected to improve the constraints on and point to a preferred model. Our work fits in this context. We ask ourselves, can a new observable such as the power spectrum of the 21 cm signal help us to shed light on dark energy? We tried to answer this question by forecasting future observations. We chose to study dark energy in the effective field theory framework. We constructed a mock dataset for P21, mimicking MeerKAT, the SKO Pathfinder observations. To this end, we modified the Einstein-Boltzmann solver EFTCAMB and the Monte Carlo Markov chain sampler EFTCosmoMC to include a new likelihood for P21. We then performed an MCMC analysis to test both the effects on beyond Lambda-CDM theories and of P21 alone and combined with CMB data. Today I'm presenting you our main results. The 21 cm signal arises from the spin fluid transition in the neutral hydrogen. This transition isn't detectable in a lab environment, but can be measured with cosmological observations. It could be useful to probe EOR, but to constrain dark energy, we are interested in the late-time signal. The observable we forecast is the power spectrum of the 21 cm signal. It can be measured through intensity mapping techniques, in which one measures the integrated emission from multiple galaxies in a very large 3D pixel. Although this technique suffers from some challenges, technical issues such as the foreground cleaning, its tomographic nature could help significantly to constrain the late-time dark energy evolution. The experiment we forecast is MeerKAT, the precursor of SKA in South Africa, which will measure 21 cm using the single dish technique. What's interesting of this telescope is that it is already taking data. So, on one end, we build a realistic dataset for P21 at the effective redshift of 0.39, hoping to have similar real data soon. On the other hand, we explore also the effects of tomography by mocking measurements at different redshift too. Okay, so the effective field theory is a standard theoretical technique. It was first applied in a cosmological context to describe inflation and later on dark energy. Recently, it was used also for a large-scale structure. For dark energy, the idea behind is to construct the most general action to be effective and unifying. Effective here in the sense to be easily interfaced with observations, and unifying to include as many dark energy and modified gravity models as possible, as special cases. I won't go into details, but just to give you an idea of the complexity of the formalism, this is the EFT action. EFT models are described by 9 parameters at second order. The EFT functions, 3 that govern both the background and the perturbation evolution, and 6 only for the perturbations. We recover clearly the Lambda-CDM model when all these functions are set to 0. Once you have the action, you can choose to study a specific model, which will correspond to a specific configuration of the EFT functions, or you can study the bare effects of the EFT operators themselves. We work in this framework and study the so-called pure EFT models. We choose to switch on the function of omega EFT, which describes the running of the Planck mass, and we fix also the background evolution. We consider different parameterization for omega EFT and constrain the parameter omega 0 EFT. In this presentation, I will focus mainly on the exponential parameterization. This decodes EFTCAMB and EFTCosmoMC are modifications to the well-known CAMB and CosmoMC to study the models in the EFT framework. Okay, I won't go into details of the likelihood implementation, but basically the main idea behind is that we modified these codes to include a new likelihood function for P21. The ingredients needed are a tool to compute theory predictions, and to this end we modified EFTCAMB to compute P21, and we need also a set of observed data. We mock 2 different sets of observations from MeerKAT, the single beam at redshift 0.39 and the tomography, what we call tomography, which means that we build a 5 beams dataset from MeerKAT observations. The model we use to compute theoretical predictions of P21 is the following. You can see our predictions at different redshifts in the plot here. In the model, TB is the brightness temperature, BH1 is the H1 bias, F is the growth rate, and P is the matter power spectrum. This kind of models for P21 has been studied and proved to be in agreement with hydrodynamical simulations. To compute the error bars, we used the telescope specifics and the telescope estimated noise. Central points are instead computed from theory and then scattered. Here you see our realistic mock dataset at redshift 0.39. I will now present our main results. We studied several different configurations. I showed the results for Lambda-CDM and for an exponential evolution of the function omega EFT. This is described mainly by two parameters, omega 0 EFT and beta. We used both the P21 single beam and the tomography alone and combined with CMB. So we ask ourselves, do we expect to be able to constrain pure EFT models? In principle, yes. As you can see here in the plot, P21 is sensitive to variations in the EFT parameters. But let's see it in more detail. So these are our results for Lambda-CDM with only the P21 single beam dataset. We find a marked degeneracy between omega C and H0, and this will be very useful when we add the CMB. We see that overall the single beam has not a very high constraining power on the cosmological parameters, but if we add additional priors on some quantities such as f sigma 8, H0, and the angular diameter distance from higher redshift 21 cm forecast, we see that results are really significantly improved. In fact, with only 21 points plus the 3 points from f sigma 8, H, and the A, we get a really competitive constraint on H0. To the previous data, we add the Planck 2018 dataset. In particular, we use the TT, TE, and EE, the low E, and the lens sync likelihoods. We find a significant improvement on the constraints of omega C and H0. In fact, as you can see here, the degeneracy between omega C and H0 occurs in the orthogonal direction with respect to the degeneracy given from the P21 alone. So when we combine the two, we have a really improved constraints on these two parameters. And yes, this is our main result. In general, we find also an improvement on also the other cosmological parameters such as NS, tau, and omega B. But the best results is for H0 and omega C. Let's now turn to the effects on pure EFT models. Here, I show the results for both the single beam and the tomography datasets together. First, we highlight that constraints on cosmological parameters remain unaffected, so we recovered what we found already for Lambda-CDM alone. Here, here I focus only on the EFT parameters. We see that P21 alone, the gray dashed line, has a weak constraining power on the EFT parameters. With tomography, the constraining power is significantly improved. In fact, we pass from unconstrained to really constrained omega 0 EFT. What happens when we add the CMB? We get improved results again. So for the single beam, we find an improvement on the parameter omega 0 EFT, which is the more significant one for the EFT models, at the level of 10%. Instead, when we use the tomography, we see that the improvement goes up to the 26% level. And in the very ideal case of very small errors, we can go up to the 35%. So overall, we find tighter constraints on the cosmological parameters, but also on the EFT parameters. So to conclude, we ask ourselves, can we distinguish a Lambda-CDM universe from an EFT one with the P21 likelihood? To answer this question, we did this exercise. We constructed two datasets, one assuming Lambda-CDM as a fiducial model, one assuming an EFT1. And here you see the comparison between the two. It's still difficult to distinguish them because if you look at the beta and omega contours, you see that they are elongated along the omega 0 EFT equals 0 axis. However, this feature, this degeneracy, is a theoretical feature and not a physical one. This arises from the form of the parameterization we choose. To avoid it, we try to avoid it, and we put an art prior on beta. Basically, we cut the parameter space in this way. What we find is really interesting. So overall, the constraints on omega 0 EFT are more symmetrical. and we find that for the Lambda-CDM mock data, the results appears to be 1.4 sigma away from 0, while instead for the EFT dataset, this discrepancy with Lambda-CDM goes up to 3.8, and in the very ideal case of very small errors to 4.5 sigma. So yes, if the universe was indeed an EFT one, we should be able to see it with P21 observations. Okay, to sum up, in our work, we extended the codes EFTCAMB, EFTCosmoMC to forecast 21 cm intensity mapping observations. We constructed a realistic single-beam dataset and a more ideal tomographic one, mimicking MeerKAT measurements. We tested the impact of P21 on dark energy models within the EFT framework. We find a significant improvement on omega C and H0, on the errors of omega C and H0 using P21 combined with CMB data. The impact on beyond Lambda-CDM models is at the level of 10% for the single-beam forecasts and goes up to 35% for tomography. Thank you so much for your attention.